Hello, and thank you for attending my lesson. My name's Mr. Johnson, and I am going to talk to you today about magnets and magnetic fields, which is a topic in Key Stage 4 or GCSE physics. It's a relatively new topic. Some of the content has been covered in the sciences at Key Stage 3, but not a lot of it. For this lesson, you don't need anything more really than a pen, paper, if you want to make notes. Maybe a pencil if you want to take a sketch of some of the diagrams, but I'm going to share my screen with you now and we'll get started. Okay, what you should see now is the presentation, magnets and magnetic fields. And prior knowledge that you should have from Key Stage 3 physics, so we've been taught in years 7, 8 and 9, you should be able to recall that the Earth has a magnetic field and roughly the shape of that field. You should recall that a magnet has a north and south pole and the behaviors of magnets, but don't panic too much because we can go through that. And finally, describe how to plot the magnetic field around a bar magnet. This is what we call a required practical, which means that it is something you should be able to describe, and it's usually worth at least 4 marks if asked in an exam for a methodology of how to do it. So, by the end of this lesson then, what you should be able to do is identify permanent and induced magnets and materials as magnetic or non-magnetic, giving good reasons for both. You should be able to describe how to plot the shape of the magnetic field around a bar magnet and what we need to do this. Finally, you should be able to describe Earth's magnetic field and explain where it comes from. So let's take a look. Types of magnet then. Magnets can either be permanent or they can be temporary. And I'm sure you all know what that means, but basically an example is a horseshoe magnet. It will always pick up a paperclip. Because it will always pick up a paperclip, we say it's a permanent magnet, it's always magnetic. This means that it has its own magnetic field around it at all times. This is different to a temporary magnet. A temporary magnet, such as a paperclip that's attached to a magnet picking up another paperclip, well, that'll only work whilst it's in a magnetic field. So a magnetic material like a paperclip can be induced as a magnet. That means we can make it a temporary magnet as long as it's in the magnetic field of a permanent magnet. We can test this. We can test if something is a permanent or an induced magnet. Because with the example that I've got on the left here, if I remove the first paperclip from the magnetic field, i.e. I take away the magnet, then the paperclips become non-magnetic and fall down. And this is a test of temporary magnetism. The rest of the paperclips are no longer magnetic, so they fall down. And if you pick one of them up and try to pick up another one with it, it would no longer work. In short then, permanent magnets are always magnetic in that they always have their own magnetic field. Induced or temporary magnets only occur or only happen when a magnetic material is placed inside the magnetic field of a magnet. If you take it out of the magnetic field of a magnet, the induced magnetism is lost and the induced magnet stops being a magnetic, which is what happened with our paperclip. So we talked a little bit about magnetic materials. What are they and where do they come from? Ask kids normally in a classroom what they think a magnetic material is or what would stick to a magnet, and they'll list off a whole range of metals, but actually there's only 3 metals that are magnetic. Iron, cobalt and nickel are the magnetic materials or magnetic metals that appear in the periodic table of elements. They're right next to each other. You can see it on the diagram there. Fe for iron, Co for cobalt, Ni for nickel, slap bang in the middle of the transition metal block. Magnetic materials are what are affected by magnetic fields. And by this, I mean that if you put a magnetic material, one of these metals, into a magnetic field of a magnet, they can feel the non-contact force. The magnet doesn't have to be touching them, but they are drawn towards the magnet. Iron, nickel, and cobalt, again, are all magnetic materials because they're next to each other in the periodic table. It makes it easy to identify them. Steel is also a magnetic material, but steel is not an element, so it doesn't appear in the periodic table. Steel is what we class as an alloy, which is a mixture of metals, and it contains iron, which is what makes it magnetic. If a material is not made of or contains one of these metals, then it's not made of or contains one of these metals, then it's not magnetic. It's as simple as that. If you don't believe me, take a copper coin next time you get a chance to your fridge, take off a fridge magnet, stick it to it. It won't stick because it's not got iron, cobalt, or nickel in. That's the end of our first outcome. Identify permanent and induced magnets and materials as magnetic or non-magnetic, giving reasons. Our second outcome then. Describe how to plot the shape of a magnetic field around a bar magnet and what is needed to do this. Now, before we get into this, we do need to revisit some of the rules around magnets. The whole thing about magnets is they have something called magnetic field, which we talked about before. A permanent magnet always has a magnetic field present. If we look at a magnet, we see what we see on the left, just basically a magnet. What we can't see, but what is around it, is the field lines that appear in the diagram on the right. The magnetic field that we've been talking about is the invisible area around a magnet, where a magnetic material, iron, cobalt, nickel, or even another magnet can feel a force. The magnetic field is strongest near the magnetic poles. Magnetic field lines extend from the North Pole to the South Pole. And this is why this diagram has been annotated with arrows to show you that actually they're extending from the North Pole and to the South Pole in every direction. So, some rules. This one, pretty much everyone says to me, sir, we know this, but it's handy to go over them again, because later on, what tends to happen is people don't understand why that happens. Magnets have a north and a south pole. Put the north pole of one magnet near to the south pole of another, and I'm sure you're all sat there at home watching saying the same thing, they will attract. We say that opposite poles, north to south or south to north, attract each other. Next rule. Place the north pole of one magnet near to the north pole of another, or the south pole next to the south pole of another, and the magnets repel. One pushes away from the other. We say that like poles, north to north or south to south, repel. And these two rules are pretty important. Please take note though, magnetic attraction or repulsion only happens when the magnetic field from one magnet comes close enough to overlap. By that I mean, if I have two magnets and one is all the way over onto the left and one is all the way over to the right of the room, their magnetic fields are not close enough together for them to interact and exert a force of either attraction or repulsion. I don't have to bring the magnets close enough to touch for their fields to overlap and for them to attract or repel, which is why you can get a magnet to either move along a table by holding one underneath and pulling it along, or pushing it with the like pole on the other side. But they do have to be close enough for their fields to overlap. This is why magnets don't behave like magnets as you increase the distance between them. If the magnetic fields are too far apart to interact with each other, then no force is felt. Detecting the magnetic field then. We can use a magnetic material in a magnetic field to line up with the field lines. Plotting compass. You may have had one of these out of a Christmas cracker or, out of a party bag. A plotting compass is essentially a small magnetic needle, made of iron usually, on a pivot. The pivot allows the needle to rotate in the magnetic field of another magnet, or in fact, in the Earth's magnetic field. So if I have a plotting compass on the palm of my hand and it's pointing north, if I turn 1/4 to the right, the needle will twist 1/4 to the left to still point north. Needle of a compass is a north pole, and so it is attracted to the south pole of a magnet. We can use this technique then. We can use this behavior of a magnetic needle on a compass to plot the field around a magnet that we can't normally see. The way that we do it, you place a bar magnet on a piece of A4 paper, just like this. Then you place a plotting compass next to the North Pole. Once you've got your plotting compass in place and it's stopped turning, put a cross or a dot on the paper with a pencil where the needle's pointing to, just like that. The next thing that we do is move the compass so that the tail of the needle now rests on the point you made. And what I mean by that is, once you've done it, move your compass so it's resting like this. Make a new mark where the compass needle now points. Then what we do is repeat this. We place the compass around the magnet at different points. So we've got our first field line there, but now I'm going to place mine there, and then I'm going to place it there and there. And I keep doing this and following the needle around. And what develops is a picture of the magnetic field around the magnet. Once you've done that, remove your compass and join up the points in pencil to show the field lines. And what you get is the shape of the magnetic field around the magnet. Something a bit like this. One of my pupils once pointed out it looks a bit like Spider-Man, or a spider, but obviously without the 8 legs. So the magnetic field lines, a complete magnetic field line diagram would look something like this, where the compass would be used to plot the magnetic field as far out from the magnet as it can. The picture opposite shows the magnetic field drawn around our bar magnet. Note this, the magnetic field lines never, ever, ever cross over each other. The closer the lines are, the stronger the magnetic field. Now this ties into what we said earlier about the magnetic field being strongest at the poles of the magnet. Between here and here, we have a fair bit of space, but between here and here, there is much less space. That means that these field lines are much closer together than these are. So a magnetic material like a paperclip placed here would feel an attraction or force, a magnetic force on it much more strongly than this one here. The other thing about the magnetic field is that the lines have arrowheads on them, and these arrowheads show the direction that the magnetic field exerts force on a magnetic north pole. The arrowheads also point, quite conveniently, from north to the south pole. The exception being this one here, which points out from the north, but because it's directly down the center of the magnet, it's not able to bend either one way or the other to get to the south pole of this same magnet. So that's how we plot a field, but how can we use the idea of a field to explain our magnetic rules of attraction and repulsion? If we take a look at the field diagram, we already know that if we bring North Pole close to a South Pole, the magnets will attract each other. The question is, why is this? If I bring my North Pole close to my South Pole, the field lines move from north to south. But because this South Pole is closer to this North Pole than any other magnet, these field lines now move to this South Pole rather than extending backwards to the South Pole of the same magnet. That means that in this region here, we have what is termed a uniform magnetic field. In other words, at every point within this region between the North and South Pole, the field now has the same strength and direction everywhere. This causes the two poles to be pulled together because they're feeling that force of attraction from north to south. For repulsion then, repulsion has a similar sort of idea going on. Here I've only used two north poles coming together. But if we bring a North Pole and a North Pole close together, the magnets will repel. Why is this? That's because the North Pole of this magnet is sending field lines out here, as is the North Pole of this magnet sending field lines towards it in the opposite direction. When these field lines of force meet, they are forced to move outward. A bit like two jets of water spraying at each other. they will splash away from each other in both directions. Because of this, the magnets push away from each other. They separate, they repel. The same is true for two south poles, the difference being that instead of the field lines trying to exit from the two poles and pushing against each other, now the field lines from the north poles of the magnets are trying to get into both south poles. Instead now they are a bit like this, where you've got your south and your south, and they're now coming in together. And because they're both trying to get in, where the field lines meet and overlap and interact, they now push each other apart to make space to allow the magnetic field lines to come into the south poles. So this explains attraction and repulsion very simply from the point of view of the magnetic field. So that's describing how to plot the shape of magnetic field around a bar magnet, what's needed to do this, and how the field itself is responsible for magnetic rules. Final part of this lesson then, describe Earth's magnetic field and explain where it comes from. To do this, you've got to remember the structure of the Earth. So a very simple diagram here. Earth's structure can be broken down into 4 sectors or segments, if you like, with the crust being the first layer of the Earth. Crust is a solid layer of rock on the surface of the planet. The thickness of the crust varies between 3 miles thick down at the deepest parts of the ocean plate to about 30 miles on land. The second layer is the mantle. The mantle is the semi-liquid layer of magma or molten rock that moves due to convection currents, and it's often the layer that escapes through cracks in the crust as lava. It's what we find in volcanoes. The outer core is the liquid part of the core of the Earth, which has a similar composition to the inner core. The inner core is the solid part. Due to high pressure and temperature, it should be metal, but the high pressure keeps it as solid. It's iron and nickel, and it reaches a temperature of about 5,500 degrees. In this, the magnetic field of the Earth, the bit that's important is the outer core, because that liquid part of the core is made of liquid iron and nickel, and that liquid iron and nickel is swirling around inside there. And there are electrical currents moving through there as electrons move through the liquid metals. So, what's the evidence for a magnetic field on Earth? Well, we've used compasses to navigate around the globe for thousands of years. A compass is a small magnetic needle, but if you take the magnetic needle out and tie it and dangle it from a string, a bit like the diagram showing, it would freely rotate until it points north. It'll align itself with Earth's magnetic field, but depending on where you are on Earth, it would also tilt relative to the horizontal ground. If you are closer to the North Pole, then it will tilt down towards the ground on the South Pole. If you're closer to the South Pole, it'll tilt down towards the ground on the North Pole. At the equator, the magnet would be perfectly horizontal to the ground. And this is because it's following the curve within the field line of Earth's magnetic field as it moves across the globe. So, compasses in the Earth. The behaviour of the compasses is evidence that Earth has a magnetic field, shaped like a bar magnet. The fact that if you take a plotting compass away from any other magnet and turn around the room with it in your hand and it will rotate to point north, proves that it's following some sort of magnetic field that's not generated from any nearby magnet. In other words, it's lining up with the Earth's magnetic field. The Earth's magnetic field is thought to be caused by the movement of charged particles, particularly electrons, in the molten iron and nickel inner core. And believe it or not, every so often, I think it was the last 800, or maybe last 200,000 years, Earth's magnetic pole flips direction. And the magnetic North Pole, at the moment, is at the top of the planet, magnetic South at the bottom, but it can flip dependent on changes in the direction of the current of the liquid metals in the core. And that takes us to our final point, describe Earth's magnetic field and explain where it comes from. So that's the end of today's lesson. I hope that you've enjoyed it. I'd like to say thank you very much for watching, and I hope to see you next time for the next one. Thank you very much.